Have you ever wondered how particles stick to surfaces, like how perfume adheres to your skin, or how pollutants attach to your lungs? This is due to a process known as adsorption. It's everywhere in our daily lives, from the way medications work in our bodies to pollutants sticking to our lungs. And it's not as simple as it seems. To truly understand this, we delve into the world of statistical physics. Well, the secret behind these phenomena lies in the realm of statistical physics, particularly in a model for adsorption mechanism. Now, you might be thinking, statistical physics, that sounds complex. But don't worry, we'll break it down. Statistical physics, in its most basic form, is a branch of physics that uses statistical methods to explain the behavior of a large number of particles in a system. Think of it as looking at a crowd from a distance. You may not be able to tell what each individual is doing, but you can certainly gauge the overall mood or movement of the crowd. This field particularly comes into play when there's a good deal of randomness involved. It uses concepts of probability to help us make sense of this randomness. For example, it's not practical to predict the exact movement of every single molecule in a gas. Instead, statistical physics focuses on averages, giving us a more manageable way to understand these large systems. So, in essence, statistical physics is about studying the big picture, focusing on the overall behavior rather than the intricate details. Now let's dive into the adsorption mechanism itself. Imagine you're at a party, and the room represents a surface. The people at the party represent particles. Some are wallflowers sticking to the sides, while others mingle in the middle. This is similar to the adsorption mechanism, where particles cling to a surface. But what makes these wallflower particles stick to the surface? The answer lies in energy. Just as we all seek a comfortable spot at the party, particles seek areas of lower energy. When they find a surface that offers this, they stick, or adsorb. Temperature plays a role too. Picture the party getting hotter. The wallflowers might start to mingle, moving from the high-energy walls to the cooler center. Similarly, as temperature increases, adsorbed particles gain energy, and some may desorb, or break away from the surface. Now, how does statistical physics fit into this party? Well, it's like the ultimate party planner. It allows us to predict how many wallflowers will stick to the walls, or how many will start to mingle as the temperature rises. Statistical physics models can calculate probabilities, helping us predict the behavior of particles in adsorption. So, just as a magnet attracts iron filings, surfaces can attract particles, leading to adsorption. And statistical physics helps us understand how and why this happens. So, what have we learned today? Well, we've dipped our toes into the vast ocean of statistical physics and discovered how it can help us understand the concept of adsorption. That's right, the very process that enables your favorite perfume to stick to your skin, or those pesky pollutants to cling onto surfaces. We've also unraveled the basic principles of statistical physics, a realm where randomness and probability reign supreme. It has guided us to comprehend the behavior of particles at the microscopic level, and how they interact with each other. Most importantly, we've seen how these two worlds collide in the statistical physics model for adsorption mechanism. This model beautifully marries the unpredictability of particle behavior with the precise mechanisms of adsorption, giving us a new perspective on how things work at the tiniest scales. And that, friends, is the fascinating world of adsorption through the lens of statistical physics. Remember, the next time you spray that perfume or see a pollutant report, there's a whole lot of physics happening right there.